Okay, I can't remember where I heard about your project, but when I did hear about it, I thought this is about the only CubeSat project going on in Australia we haven't yet heard from on campus, so let's find out about this one. So I contacted Lee and invited him to come along, so we're interested in hearing what you've got to say.
Yeah. Thank you for inviting me to come along. So I'm going to tell you about a CubeSat project. It's a 6U CubeSat. It's kind of at the very preliminary conceptual phase. What we did is we kind of put together an ARC leaf proposal earlier this year, and so the details that I have for you today are kind of limited. We don't have anything specific. All we did is our homework to make sure that the funding proposal that I put forward was actually feasible. So I'm afraid I won't have too many details, but I'm looking forward to your input. The other caveat is that I'm an astronomer, so this field is very new to me. So I excuse the jargon, or I might mess up some of the jargon. But again, I'm looking forward to your input and maybe sharing some of my enthusiasm for this project, because I'm really excited about what this can do for me as an astronomer in terms of doing my research, studying very distant galaxies. The people listed here are the people that kind of contributed the technical information that I'll be presenting. So Anthony Horton is kind of the co-PI. He's based at the Australian Astronomical Observatory, and he works on telescopes. And so he's the one who's really designed the telescope that we're going to put into this mission. Sam Eisenfield at Macquarie University, he's our communications expert. And he's designed or come up with a preliminary design for what we're doing here. Mike Petrovic and Robert Franzen are based at ANU, and Mike has helped with the engineering side of things, the budgets, and Roger's kind of looked over the project overall. So I want to acknowledge them. I'm just the astronomer again, so I'm excited about doing the science, but these guys are really doing a lot of the work. So my talk will first start with the science, so the thing that I'm excited about doing, how can a 6U CubeSat putting it up into space actually allow me to do things I cannot do from the ground. That will set up the mission requirements, the constraints that we have, which will then dictate or constrain the science payload, the communication systems, and the attitude determination and control topics, which I'll cover briefly towards the end of the talk. So a bit of background. So astronomers for hundreds of years now have been building bigger and bigger telescopes. What we typically use are very, very large mirrors. This is the kind of culmination of that effort. This is going to be a telescope that will be put into Chile. It has a mirror in the center here of 39 meters across. It'll be the biggest optical telescope in the world, and it's going to kind of revolutionize astronomy. So this is kind of what we've been headed towards for a long time. But there's something that this thing cannot do that a small kind of off-the-shelf Canon lens can do. And that's actually taking images of really faint astronomical targets. Let me demonstrate with an image. This is an image taken with the Hubble Space Telescope. The dots here are galaxies pretty far away. The central point is actually a galaxy that's about 13 billion light years from Earth, so extremely far away. It exists, or the light that emitted from this thing existed only 1.5 billion years after the Big Bang. So it's a really interesting thing. Hubble is great for looking at these objects, understanding what the universe was like when it was young. So Hubble and the large telescopes like the one I just showed you are really good at imaging really faint, compact things. But if you take that compact thing and kind of spread it out over an image, so if you take this object and spread out all the light across this image, Hubble and other large telescopes no longer can detect it. What happens is this mottled structure you see in the background is noise. It's noise from the detector, it's noise from the counting statistics from the sky background, but it's also because every single one of these objects of light scatters a bit of light everywhere on this image. So even this one impinges a little bit of light in this region here. Now we can try and remove that effect and calibrate it out. But the trouble is with a very large telescope like the Hubble, the one I just showed you, it's kind of impossible to clean an image from all that stuff. And so this is where a new way of observing, actually a very old way of observing, has kind of come back into style. And that's using, instead of a big mirror, using a refracting telescope. So just like a lens, like in your iPhone or whatever. Why are big telescopes a problem? Well, here's one picture here. very large telescope, light comes in from the top, hits a big mirror on the bottom here, bounces back towards the top, hits the secondary mirror, bounces back through the system. The trouble is, as the light passes through the system, there's big support structures in the way, holding up the top of the telescope. As light passes through there, light is kind of scattered around, and what you get when you take an image of a bright star are these diffraction spikes, which are shown in this image here. Why is that a problem? Well, every single dot or source of light on your image, even these really faint things, is doing the same thing. And they kind of collectively set this background noise. It's a systematic noise that's almost impossible to remove when you have a big support structure in a way. Another problem with traditional reflecting telescopes is that the mirrors are not perfect. So the surfaces bounce light pretty well, but not perfectly well. And so the final image can introduce this mottled structure, which you see on this image here, just from imperfections on the smooth surface of the mirror. So those are two main problems. And it's kind of limited what we could do in terms of imaging really faint things, so really diffuse things, or in the field we call it low surface brightness imaging. Why is that interesting? What can we learn by imaging really faint, diffuse structures? Well, this is a picture of a galaxy. It's probably my favorite one. This is the Sombrero galaxy. And that's a typical image taken with Hubble Space Telescope. This is a computer simulation of stars within that galaxy. And this is kind of mimicking the observer's view. This is what we see in terms of the stars. The blue structure is the light we see from the stars here. Now in the simulation, we can go to fainter levels, more extended, and what you find is there's more extended structure in the simulation that you just can't see with modern telescopes. So as I flip to fainter and fainter levels, what you'll see is this kind of wealth of information that we just can't see right now with the traditional telescopes. What is this stuff? Well, this is the signs of how this galaxy actually formed. We believe gravity kind of pulls in smaller galaxies, smaller stellar structures, lots of stars, and this galaxy kind of grows by just eating up lots and lots of small galaxies. As it does it, the gravitational interaction kind of kicks out stars, and it takes billions of years for these kind of small galaxies like this one here to kind of leave a trail of stars along the path. By looking for these things, you can start to recover the history, what's happened to this galaxy in the past. And that's exciting for my work, because I'm trying to figure out how galaxies formed from the Big Bang until the present day, over this 13 billion years. So this type of work allows you to access a whole new parameter space that we just didn't have access to before. So what's the key innovation for this Australian Space Eye and my work? Well, it's actually making use of kind of off-the-shelf Canon lenses. So again, a refracting with no mirrors. All the light does is just passes through these really well-made pieces of glass, focuses onto the camera, and it allows you to recover the faint structures that you can't see with larger telescopes. So this was not my idea. This is an idea that was kind of put forward by a team just in 2004, last year. They demonstrated that if you do this, you take a bunch of relatively cheap Canon lenses and observe a galaxy, you can see this new structure that you just couldn't see before. So this has gotten astronomers very excited about this because we now have access to this information that we just didn't have before. So it's kind of neat when you think about it. A tiny little lens, it's about this big. It still costs about $12,000, so they're kind of expensive. But it's a lot cheaper than this multi-billion-dollar project. And it can do more or different type of science that this thing just can't do because of that sort of support structure and the mirror-based system. The Canon lenses are great too. They have special coatings that minimize the reflections on all the lenses. So they use this special coating that they put on the lenses that reduces the reflection, which you can see in a lens that has the coating and it does not. Any reflection that you encounter increases the chance that light's going to bounce around, and on your final detector, your sensor, it's going to ruin the image and make it very difficult to detect any faint structures. So the Canon lenses are really well made and they really do serve the purpose. This is a picture taken by the North American team. Typically in astronomy, you kind of get out to this colored region in this image. What they've been able to do is map really far out. This gray structure are stars in this galaxies, and it allows you to see what's going on in this galaxy in a lot more detail. Here's another exciting object they found. So here's kind of the classic galaxies, the Sombrero, like I showed earlier, some other well-known ones for astronomers. This thing right here, they discovered this thing. No one has ever seen anything like this before. what it is a galaxy. It's big. These are all to scale. So it's as big as this galaxy here. But the number of stars in it is so low. It's like a big star cluster, maybe 10,000 times smaller or 10,000 times less stars than is this galaxy, but spread out over that entire region. And so you can see why the low surface brightness imaging is really a new parameter space. We just haven't seen these things before, and they really do tell us something profound or interesting about the universe that we live within. So what I'm trying to do here in Australia, about a year and a half ago, I came up with my own version of this and I Australianized it, called the Huntsman Telephoto array. You can kind of see the resemblance there. And what I'm trying to do is more or less what they're doing, but trying to do different things. So with the AAO, we're working on the instrumentation side of things and trying to innovate on the original design and do new things. At the moment, we only have a single lens, so we're calling it the Huntsman Eye, because we only have one eye for the Huntsman. This is it pictured in the labs now. We're aiming though to get a whole array of them working together, because one lens is kind of slow. You just don't collect enough photons, and with 10 or 12 of them, you can be 10 or 12 times more efficient in collecting enough light. Even with 12 lenses, though, it takes about 2 weeks of continuous observing at nighttime to actually get one galaxy target. There's not much photons coming off this stuff, so it does take a lot of time. So I've got enough money to actually put a permanent dome up in Coonabarabran, New South Wales at Silent Spring Observatory and install about 3 to 4 lenses in early next year. And so this is the kind of ground-based project that I'm now working on. So this brings me to the Huntsman in space concept. So Anthony and I at AO were doing this ground-based system, and I thought I'd share this little thing here. So Anthony is very prolific on Facebook. He actually publishes a lot of things. And it turned out that Matthew Cullis at ANU actually was following Anthony and saw what we were doing with the ground-based Huntsman facility, or at least that first lens that we do have. And he posed to us in Facebook, or to Anthony, what would you do, or how could you do things better if you were actually putting a lens up into space? And this triggered the concept, the mission that I'll be talking about today, the Australian Space Eye. So I'm not really a Facebook person myself, but I do now appreciate the value of sometimes broadcasting your research in these channels, because you never know who's listening and who might actually come up with a really interesting thing to do. So Matthew Cullis at ANU kind of hosted a meeting called the Astrostats meeting last year in December. What he asked the community to come up with was astronomy missions that they could do from space. And there are about 10 of us. We each gave maybe a 5-minute presentation. And then the workshop or the group kind of picked projects that were, 1, scientifically interesting, but 2, most importantly, could actually fit within the grant schemes that we have here in Australia. So a kind of grassroots small project that was cheap enough that you could actually fund the whole thing using the ARC. So our project was selected with one other to actually meet those requirements, an exciting science case, and also maybe fitting within the Australian grant scheme. So this is the Australian Space Eye. This is the mission that we've kind of come up with. What it's aiming to do is do really low surface brightness imaging from space. So pointing up at very distant galaxy targets, trying to see things that we just haven't seen before, and things we can't see from the ground. So what are the reasons, or why would you want to put a Huntsman-like system up into space? Well, the key thing is the wavelength region. So this is just wavelength from the optical UV into the infrared. This is a plot just showing the size or the area of a telescope and the ratio between the ground-based area of a telescope and a space-based telescope aperture. The area, of course, dictates how much light we can collect. And as you can see from this, in the optical, it's pretty efficient. So a space-based telescope of a given size is pretty much competitive to the ground. That's because the atmosphere above us is transparent. Light from in the optical just passes straight through. In the UV, the atmosphere becomes opaque to UV light, and so it's actually more competitive to go into space eventually and do UV imaging from the ground. Same thing in infrared. The infrared wavelengths of light get absorbed by the atmosphere, and also the infrared skies are really, really bright, and so it's very hard to see the faint things that I'm really interested in seeing. So One motivation is to get out of the optical to see at other wavelengths of light, which gives us more information. As astronomers, all we have is light coming in. We can't interact with the galaxies, so what our tool set is more or less the wavelength spectrum, which is shown here. So we considered going into the UV and also the infrared, but we've chosen with the infrared. Now we're not going very far into the infrared. If you go to 10,000 angstroms or higher, the detectors, or the sensors and imaging sensors that we use in astronomy are very, very expensive. So we've kind of focused on this sweet spot here, better than the optical, but not too far into the infrared, to keep the costs down. So that's one motivation. The other key thing is that at infrared wavelengths of light, the sky is a very dynamical structure. So this is an image taken at 0.8 microns in the infrared, covering about a 20 by 20 degree. It's just a snapshot of the night sky. What you'll see is this kind of structure in the night sky. It's not clouds, it's actually just the atmosphere. It's kind of glowing at these wavelengths of light, but it's not glowing in a uniform pattern. It's kind of spread out and gives a structure, which makes it very difficult to, again, detect the faint structures that I'm after, because it's a kind of comparable level, or the variations are at a comparable level of what I'm trying to measure. So this is a big problem when you're trying to observe at infrared wavelengths and get really faint structures like I am. Another issue with this particular wavelength region is that it varies as well. So that structure just doesn't stay the same. If it did, we can kind of model it out. This is an illustration showing the same wavelength of light. Again, a piece of sky. There's 3 stars which are indicated there. But over a 50-minute period of time, you see the same region of sky does vary. And that's another big problem if I'm trying to remove any effects or any kind of structures on really faint scales. So this is another big thing. The final issue with observing from the ground at these wavelengths of light is there's also absorption molecules in the atmosphere that actually absorb these wavelengths of light. And again, they vary on temporal and spatial timescales. This is a time plot on the x-axis showing altitude, and the color density indicates the number of aerosols at each altitude over a 90-minute period of time. You can see how they do vary over this period of time, which is kind of typical for your observations. This black curve shows the transmission, how over at one point in the sky, how many relative photons are actually reaching your detector on the ground. The value of 1 is about here for this normalized graph, and you can see over this 90-minute period, the variations are of order of a few %, and that's exactly the kind of thing that we're trying to avoid by going up into space. So the main advantage of going into space for this particular project is to minimize the spatial and the temporal fluctuations in the brightness and also in the absorption of from the Earth's atmosphere from an observed wavelength of about 7,000 angstroms. So this brings me to the project, or the main idea. So we want to get above the atmosphere to see what we can see in very distant galaxy targets. This is the aim of the project, simply to do really low surface brightness imaging at a new wavelength and see, do some really cool science, which I'll talk about in just a second. So this is kind of now a summary for the rest of my talk. I'll step over 4 key things. The first one has to relate to the first requirement, which is actually keeping the costs down for this mission. As you all know, funding is hard to come by, especially through the Australian grant system, and so we're really trying to put forward a really exciting science case so that we're awarded the funds to actually execute this project. So I'll start with that one. How do we keep this mission relatively low cost, and how do we get enough money to actually fund it? So the key science and the thing that I'm excited about doing is to not look at galaxies, to actually look between galaxies. So you might kind of wonder why, what is there? And in the images that I've shown, it's just black. There's absolutely nothing that you can see in terms of structures when you look between galaxies. But there's this thing called the infrared background light. This is a plot kind of showing wavelength again, and showing a few different regions. So from gamma rays to X-rays to UV, infrared, microwave, and then radio. What this shows is that if you look between the stars and the galaxies at just flat, blank space, you still detect things. There's this brightness level that's kind of constant in every direction. You might have heard of the cosmic microwave background. That's the one that's shown here. That's the afterglow of the Big Bang. And so that, is a very fundamental measurement to make. If you move just a little bit to infrared wavelengths of light, people have detected this excess from sources they can't see directly, but there's just kind of this background level. And so the question is, and the interesting part of this is, what's causing that? What sources of radiation are kind of essentially everywhere in a uniform pattern, but shining so faintly that they contribute to this background? What are the sources? Well, this is a timeline showing from the Big Bang at the top to today, about 13 billion years, just showing a compressed timeline of the major events that have occurred. So Big Bang at the top. What happened after the Big Bang? The universe was just filled with hydrogen. It's neutral hydrogen. So any photon of light would encounter a bit of hydrogen, and it would just stop. It couldn't travel anymore. And so this period of the universe is very opaque. Light couldn't travel anywhere. And so it's a really interesting period, but it's also very difficult to study. There's this period, though, when that hydrogen gas started to burn off. It started to ionize, and that was from the first sources of UV radiation. So the first stars, the first galaxies to have formed. What these did is they ionized all the hydrogen, and eventually, about 1 billion years after the Big Bang, the universe became ionized hydrogen. So light all of a sudden can travel without encountering neutral hydrogen all the way to our telescopes today. So we can very directly see what's happening in this portion of the universe for the last 13 billion years, 12 billion years, by using telescopes. Light emitted here travels that long period of time, and we can look back in time essentially. But what happened before this is really hard to understand or to study directly. And so what this project is trying to do is actually look into this period and look for these first sources that are thought to have kind of ionized the universe. And this is really important because it kind of sets the stage, the initial conditions for the rest of the evolution of the universe. So by looking for things between galaxies, we'll start to see these really faint structures that we know should be there because we're pretty confident on how the Big Bang progressed, but we haven't yet seen them. So what we're looking for are these first UV sources, the first stars, the first galaxies, and looking for this kind of background level in space. So why is low surface brightness imaging important for this? Well, this is a typical image taken with the Hubble Space Telescope. When you really zoom in with the Hubble, you see lots of stuff. I mean, there's just galaxies and galaxies, some bright stars in our galaxy, but most of these are very distant galaxies at every single location. So if you try to look between these things at the background, you can kind of mask out the brighter sources and remove them, but you still see that there's this structure. It's actually hard to find a region in this image where it's truly dark. That's because the telescope, the way it has these diffraction spikes, scatters light all over this image, and it ruins that faint structure, and it makes it really difficult to find things out there that we're really trying to find. So this motivates the Australian Space Eye. This type of work, though, is not new. There's actually a project based in America and in Japan called the Cyber Mission, and what they're trying to do is the same thing, but they're using a sounding rocket. So they have this, I'll show it here, a science payload that consists of a few imager, a spectrograph, to actually make these measurements that I've been talking about at infrared, or actually longer wavelengths of light than what we're focused on. But this is launched on a sounding rocket, so it goes up for a few minutes, takes a few quick shots of the sky, and then comes down. Now they do this a few times. They've run this one, I think, 4 launches, and they collected enough data to do this. The trouble is, though, that their systems were not optimized for low surface brightness imaging like ours will be. And so there's a problem with that. I mean, the signal that they detect could actually be these diffraction spikes that I've been talking about that are actually mimicking the signal, and they aren't actually real. So we're trying to go above and beyond what they've done and try and do some really interesting science. Another key thing about our mission is we're not going to get only 40 minutes of observing window. We're going to be up for hopefully a year, maybe 2 years, and actually collecting a lot more data than they are. So let me talk now about the science payload. As I mentioned, we're focused on low surface brightness imaging, so we're going to include a refracting telescope, not a traditional mirror-based telescope that's optimized for what we're trying to do. So for this kind of work, one of the serious problems with a refracting telescope and the kind of observations that we want to take is that you need a relatively long focal length. What this means is you more or less need a zoom on the field that's not too big, but not too small. You need this kind of sweet spot to get enough of the universe, but not too much. And so for this, you need a special configuration that has a relatively long focal length, kind of like this telephoto telescope, which is shown here. It also is important for the imaging sensors that you can find for relatively small amounts of money. It's just kind of an important optimized system. It's going to be optimized for reducing any form of scattering of light as the light passes through the system. So any glass needs to have special coatings that minimizes any reflections. You need baffles to make sure that earth shine or sunshine does not get into the telescope, and again kind of bounce around and ruin the really kind of pristine images that we're trying to make. Another key thing is that our solar system, in the disk of it, there's actually dust kind of just scattered around, and the sun hits it and it bounces back towards us. And so we have to avoid the solar system. That's another important constraint, and we want to look off of it as much as we possibly can. There's also the Milky Way galaxy. That's also kind of an annoying target for this kind of work. So there's just way too many stars. You can't see between them. And so we have to be off the same plane of the solar system as well as the Milky Way. And so that kind of limits to the poles of those two systems, but there's still some fields that we can consider. Another key thing that kind of spans all astronomy is the most interesting targets are always, there's very few photons coming through, and so the whole system has to be optimized for that. We have to take that into account. So the platform that we're using, so ANU has signed an MOU with Tyvak, the co-founder of the CubeSat platform, started a company called Tyvak, and they're kind of coming up with these systems which you can buy as a complete package. They have all these subsystems already installed. I think you can customize if you want. But it's going to be a 6U CubeSat. That's what we need to actually fit the actual main payload in. So this is a schematic that Anthony Horton came up at the AAO with. The top section will be 2 U's of that will be just the basic infrastructure that we buy from Tyvak. 1 U at the top here is maybe empty or maybe can be used for something else. And then the telescope will occupy most of this bottom region, which is shown here. And here's a cutaway internal view. And here's a view showing the optical path, so light coming in from this side through the baffle. And he's come up with a model for the optical telescope system. He only needs 5 lenses in an array, which is shown here, to actually focus onto the sensor that we're trying to use. A related concept to this is the orbit. So I think we're going to go with a sun synchronous orbit. There's a few advantages. The key one from a science perspective is actually minimizing thermal variations across the CubeSat. By being always in the sun, you can kind of rotate it. So let's say in this model here, the top of it is always facing the sun, and so the thermal gradient across this thing is kind of constant. This is important because telescope optics, you need to focus them, and any movement on a spacecraft is not a good thing to do. So we're trying to minimize that and the need to focus due to those thermal variations. So that's a key thing to consider this particular mission. It's also a popular orbit, so we probably can get onto more rockets at this altitude or this orbit. Solar power is useful, and again, it accommodates one of our requirements to observe off the solar system plane. Not perfect, of course. You'd actually want to go around the equator to always point off the plane, but the thermal stability is actually quite an important thing. So we're willing to have the Earth clipped, get in the way every once in a while. It also might be important for the communications or the data transfer rates. We might need a break from collecting data to actually transfer it down to the ground stations. So here are the details on the scientific payload. Anthony Horton has come up with a system that has a 480 millimeter focal length, but that fits within the 3 U's of that CubeSat, maybe 2.5 U's. The aperture, of course, is set by the size of the CubeSat, so a relatively small aperture for what we're talking about, but it still is enough to collect enough light. With the imaging sensor, which we've kind of selected maybe, a CMOS imager. The telescope means that each pixel will correspond to about 3 arc seconds and span a 1.6 to 1.25 field of view, degree field of view. The CMOS detector, this one's actually going to be used in a mission, a CubeSat mission. So the imaging sensor, which is what we think of going with, is pictured here. It's a CMOS detector. In astronomy, we typically still use CCDs. The reason is that CCDs generally have lower read noise and dark current, and that's really important if you're trying to image something really faint and it's not delivering enough photons to overcome the noise from those two things, then it's completely worthless. So that's why astronomers have been using CCD imaging sensors for a long time. CMOS sensors are starting to get pretty good though, and they're catching up and are probably good enough for what we're trying to do in this mission. The dark and the read noise currents are given up on the top here. Yeah, it's also what has been selected for a Janus mission, which is a high-resolution camera, which I believe is going to one of the rings of Jupiter. So the communication systems, that's the next component. What I'm going to present here was actually presented recently at 2 conferences, the Australian Space Research Conference in Canberra and an earlier one up in Queensland earlier this year. Sam Reisenfeld, an associate professor at Macquarie University, is the person who put these numbers together. So I don't know a lot about them, but I'll still throw them up in case you're interested. To estimate how much data we'll be producing for our mission, here are some numbers. So we're going to be taking 2-dimensional images of the sky. The number of pixels are given there. We'll compress them to reduce the required transmission rates. We can squeeze in about 4 images per orbit. This is primarily because the exposure time per image is about 10 minutes long. So we start taking an image and we wait about 10 minutes. And again, this is to collect enough photons from our sources to overcome the base level read noise and the dark current from the detectors. It also reduces the transmission rate, but if you integrate or collect data long enough, what starts to happen is cosmic rays start to hit the sensor and ruin parts of the image and make it unusable. So you can't integrate forever. There is a limit, and then there's probably a sweet spot that is still to be worked out. But the key thing is that we do have to take long integrations, about 10 minutes in duration. That's pretty standard for something like the Hubble Space Telescope. So with only 4 of those 10-minute exposures per orbit, and let's say 16 minutes to actually transfer that to the ground, the required transmission rate is about 100 kilobits per second. So Sam has come up with a preliminary design for the CubeSat communication systems. So an S-band 2.25 gigahertz system with a 5 dBi gain antenna, relatively small transmit power, and some losses and modulation is selected. It's also mocked up some preliminary Earth station design systems, just kind of, again, coming up with an average system that you might expect to encounter. We'll obviously make use of a whole range of these ground stations, and so this is maybe the average. So he assumed that a 1.9 meter diameter, efficiency factor, which is given there. He's considered the geometry of the situation well. It feeds into, of course, how long you can actually transmit to that ground station. And yeah. And so he's pushed it all into his equations and come up with a single number, the link margin. So this is just kind of a first order feasibility study to show that the requirements that we have in terms of data production and the typical ground station might actually work. Details to be determined. He's probably going to be looking into modeling what the realistic ground station situation is like. Can really interface with them for 16 minutes per orbit? Is that actually possible? He's also interested in looking at encoding mechanisms to maybe deal with different kind of air transmission rate algorithms. So you can check out these details on the published paper here, and I believe this one will be published pretty soon. The next subsystem that I want to talk about is the attitude determination control system. So this is a picture that I've taken with the Huntsman Space Eye, the thing that you get from the ground. Typical galaxy image. This galaxy is not too far from us, but not too close either. This kind of gives you a visual impression of what you'll be encountering on a typical astronomy image. Bright stars, very distant galaxies, the little red things in this image, and then maybe a galaxy in the center like this. The key thing for this, though, is that we took 5-minute exposures. So just like I was mentioning, from space we're going to maybe do about 10 minutes. On the ground we still do take quite long exposures. And from the ground we have very specialized telescope mounts that maintain the pointing over that exposure time. When things go wrong, when that tracking from that telescope mount stops or is kind of uncertain, you really start to see it in these images. You get these star trails tracking all the stars kind of drift across, and it more or less makes the data unusable. The key thing, though, is that you need to maintain a really accurate pointing system, very stable, for the space eye within 3 arc seconds, which is about 1 pixel. So we want to keep one source of light onto 1 pixel as much as we possibly can over a 10-minute typical exposure time. And that's the challenge. When we presented this in December at ANU, I'm sure you all know this, this just has not been done yet, as far as we know, for a CubeSat platform. So this is one of the key challenges for the mission, where we don't have a demonstrated working solution. But we do have some ideas which I'll share with you now. I'll first go over some options for attitude determination. So the CMOS detector the imaging sensor that we're going to use, has a neat feature where you can actually use sub-windows and read out those sub-windows at different rates. So most of this image will be read out in the blue area every 10 minutes, but you can have sub-windows where you put stars, or you find stars and you put them onto these sub-windows and read out at a much higher frequency. This then delivers pointing information on how the tracking of your CubeSat is doing, and then feeds back into the system to correct for that. So this is one option we're considering. Of course, it kind of ruins sections of your image. Unfortunately, the way it works is that you can't just focus on a single star. It reads out this entire row here. And so we might have to trade off some of our imaging area if this is the solution that we want to go with. Of course, the other one is to use a dedicated imaging sensor, either near the focal plane of the telescope or off the side. So that's what we're thinking for the determination. So as I mentioned, and I'm sure you're fully aware of, the control using a reaction wheel, just off-the-shelf stuff, even for a CubeSat, is just not accurate enough. It doesn't keep that stability down enough. So I think the Tyvak number is 0.5 arc minutes, RMS over typical duration. And because we're trying to get down to 3 arc seconds, that's a big problem. So 2 possibilities that we have kind of explored in some very little detail. One is to put the imaging sensor onto a platform that moves in the XY direction. So you get information about the pointing system that feeds in and then corrects for that motion in kind of real time. Another option, of course, is to use thrusters, and thrusters technology is kind of really coming along in this area. So to show that first option, this is a concept that's been published for a CubeSat mission called ExoPlanetSat. I don't believe that they've launched anything. I haven't seen anything on their work in a while now. But they have nicely documented one solution that we could possibly use. And that's, as I mentioned, to use this platform where you have a lens, a detector in the back here, and between them you have this piezoelectric stage which moves in the XY direction and compensates for any motion with the spacecraft. So in the focal plane, for example, you could have the science imaging sensor up here, maybe a small star tracking up here, and the aim for their mission, and our mission as well, is to keep within 1 pixel all the light at that one location. You don't want the light source to be drifting between pixels, because that just ruins what we're trying to do. So they've demonstrated in a lab how a classical system introduces quite a lot of motion that they need to compensate for. When they turn on this XY stage, they can bring down the random motion from that motion down to very small levels, within 0.05 pixels for their system. So for this system, they have fairly large pixels for this test bed. Our pixels are going to be a bit smaller, and so if this works, then this actually might be a good solution. The trouble is, I think the duration for this was relatively short. It's not clear if you can maintain this over a 10-minute duration. You might have a lower frequency kind of drift that's not accommodated by these high-frequency spatial variations. There might be a drift that we need to worry about. It just you can't do with this type of system. So details to be worked out. The other option, of course, is using thrusters, and so there's a lot of activity from commercial companies and people here in Australia on developing cheaper, more economical thrusters. This is just one example that will be available next year. Small enough to fit into 1/3 of a U, so small enough and perhaps delivering enough impulse and having enough fuel reserve to actually do what we need to do. But again, details to be determined, to be worked out. But this might solve that other problem of making sure that the drift of the system is not a problem. Another issue with the XY stage is that there's, for every action there's a reaction. If you're moving something around, it might actually be introducing this larger scale spatial movement into the system. So again, we need to work this out on a realistic CubeSat environment. Tyvak, though, who's partnering up with ANU, have kind of claimed that they can do it. They haven't demonstrated it yet, just using thruster technology. They have a mission called CPOD, which is aiming to put 2 CubeSats up that will kind of rendezvous, do complicated maneuvering systems, and actually kind of link up. It's mostly aiming to demonstrate this project, and they're going to launch it, I believe, next year. And so they're going to share with us this imaging, the spatial information, the spatial variations that they measure from their CubeSats, and their ability to cancel it out. So that's all I wanted to share. I'll just finish up with a timeline of the project. So hopefully, if the funding application does go through that I led earlier this year, we'll start work right away on the design initially, and then actually starting to bring the components together, testing them on the ground. We'll use probably the Huntsman on the ground system to test the little telescope to make a direct comparison of how observing from the ground with the same telescope compares to observing with that telescope up in space. We do need more funding. The LEAF scheme does not pay for everything, so I'll be looking for more money next year, and also refining the science objectives. So phase 2 will actually be taking the CubeSat platform, stuffing everything in, and launching it, hoping to launch in 2018 if we get funding in the next month. And we're aiming for probably 1 year, maybe 2 years duration in space. If you're interested in this stuff, we do, as I mentioned, have a social media component. So this is mostly for the ground-based system, but it's definitely starting to have a lot more about the space-based system. And so if you're interested in what I do in terms of my research and the types of stuff that we're developing at the AAO, please follow along here. We had 2 students over the winter, an ex-graphic design student who came up with this logo, which is shown here, kind of cute. So I'll just leave up a summary of the mission requirements to get you to think about the challenges that we have. There's a lot of challenges in terms of maintaining that stable pointing. Communications, we kind of came up with a rough estimate to show that it works, that it's maybe feasible, but the details are definitely to be worked out. We have a relatively high data rate, and so this is going to be probably a challenge for the CubeSat platform. The platform itself is constrained by the science payload, having that large telescope, relatively large telescope in there. But the key thing, and I think the exciting thing about this project, if we can actually demonstrate that we can fit a CubeSat project, a fairly large one, a 6U, into the Australian grant scheme, that might be an exciting thing for the entire community, and demonstrating that we can do it and actually make it happen. So thanks for your time, and I'm happy to take any questions.
If you've got a, this might be not something that you guys have, might be looking around, but if you guys have got such a high attitude determination requirement, high sensitivity. And you talked a bit about having sensors on different phases that not necessarily on the same optical phase. Have you guys considered, I suppose, the thermal expansion of the structure, how that might, like, given the sensitivity you guys require, how that might ruin? Because if you're to put the sensor on the opposite end, like the rigidity of that structure, especially with the thermal gradient, might not be enough to constitute accurate reading.
Yeah, that's a good point. So if there's a thermal gradient and if the whole thing is kind of flexing back and forth, then I think that would definitely be a big problem. That if you're not monitoring the imaging sensor, that would be a big issue. So yeah, very good point. I guess if we do get the sun-synchronous orbit, maybe that thermal gradient is going to be relatively stable and maybe it'll be okay. But yeah, very good point. I hadn't thought of that.
I've got a question on that pointing as well. You're trying to keep objects just get them to eliminate single pixel technology. If you're then using the same CCD as your feedback mechanism, you actually need objects to have an extent that's greater than 1 pixel in order to get an error message, right?
Yes.
So
That's not going to work, is it?
yeah. I mean, even your control system would have sort of smaller angle pixel.
Yes, that's an excellent point. So I think we tossed that issue came up, but kind of said we'll figure it out later. But that's a very good reason why that option would not work, because you do need sub-pixel information.
Observing objects that were bigger than a pixel, you might still be able to do it, but most of your objects are going to be pixels.
Yeah, there will be. Maybe if you have enough of them, let's say. And what happens is naturally if you have random stars in the sky, they're going to hit different parts of that pixel. So one will be in the center, one will be on the side. And maybe by using 3 or 4, maybe 5 different stars, maybe that's a way to get, higher spatial resolution than you could with 2 pixel.
Sub-pixel resolution is half of the applications.
The sub-pixel resolution requires you
That was on the center.
Yeah, you're right. So you can get sub-pixel information from the larger. But the aim of this mission is to reduce the footprint of any point source. Because naturally the optics will, and the diffraction limit will spread it out. But we're trying to keep that spread out bit to 1 pixel. So we're actually, there's a science driver to put it all within 1 pixel. And then you don't have the good centroid. There'll still be some flex, but maybe not enough. Yeah.
How do you manage the aberration you get from the lens?
The aberrations?
Large, you get an aberration. How do you manage the aberration?
Do you mean just in the...
Like the colors diffracted?
Yeah, good question. So in astronomy, what we typically do is we don't try and take a broad spectrum. We actually try to break it up. And so then you get flux at different wavelengths, and that's what we have. And that's how we determine if that's a young star or an old star. And so what we'll have on this system is probably 2 filters that will actually probably ideally be coded onto the imaging sensor themselves. And they'll just capture maybe 1,000 angstroms each of a particular wavelength band. And in that case, over maybe 2,000 angstroms, Anthony's kind of determined that the reddest part and the bluest part will probably hit the same part of the imaging sensor. So, yeah.
This is a little bit of a technical question, but it's sort of commercial as well. There's a company called Headwall Imaging.
Headwall?
Headwall.
Yeah.
Yeah, I think I got that right. And they use holographic diffraction ratings to correct for aberrations for their sensors. So these, basically what they do is they take the lenses and then run them through, shoot lasers through them, which are highly collimated, very well known, and then generate holograms. And then they run the final image through the hologram to reverse out any aberrations in the lens. Is that the kind of stuff you guys do?
So it's actually within the lens you
Yes.
print
Correct. So in your image there, when you show the spacecraft, and you show the capture at the front, and then how it goes down to the detectors, they introduce a holographic diffraction rating. to reverse out any extra aberration.
Interesting. No, I'm not aware of
Not aware of that?
that particular purpose. We always put coatings on these things to minimize reflections and things like that, and to compensate for this somewhat. But it sounds like that's a more advanced, sophisticated way.
I'm happy to share it after it's done. I just
Yeah.
came across that. I'm no expert in optics whatsoever.
Yeah, no,
but I thought it was kind of
sounds
cool. Get out of jail.
As long as it doesn't bounce light around. That's the thing that we're trying to avoid at all costs. So yeah, interesting.
It may, I don't know.
You might have familiar with Arcos star catalog.
Hipparchus catalog? Yep.
Well, the optical capture system is really quite interesting. It didn't use an image sensor as such. They actually had a screen in front of raster on the range. So they were able to, extremely sensitive detect on each point. Another advantage we have is it just tunes particular wavelengths. So I'm just wondering whether you consider that particular approach rather than using a single sensor.
Let's see. I think for that mission, astrometry, so the positional accuracy is like key. We're trying to measure the motions of stars over many years, and that's really hard to do. And so I have a feeling that that's probably overkill for our mission in terms of collecting that kind of information. They're going for extremely fine spatial differences, where we're just trying to do some pretty crude ones over the pixel scale. They're going for sub-arcsecond levels. We can accommodate 3 arcseconds or so. But yeah, I have heard about this system lately. Very interesting.
Has Tyvak given a ballpark idea of cost?
For their platform?
Yeah.
I think it's about $500,000.
Okay.
Yeah.
That's the whole mission cost, or just?
No, just for their platform.
Oh my gosh.
With integration services?
No, but don't quote me on this because I don't know the details of that. I did not do the budget, and so I don't know what's involved with that.
I think I know the answer to this, but when were you hoping for your response to your grant application?
In the next month, it's
Next month.
Yeah, within the ARC thing, and they say October, November. Surprise! So it was a big surprise when it actually comes out. So fingers crossed. Most of the budget is people, not equipment. Launch is expensive too, but it's mostly just people. So, yeah, more expensive.
I sort of missed some of your argument at the beginning about reflective telescopes. Because all of them, looking at the big one that showed all the ones in space and reflective.
Yes.
And yet looking at a relatively small fragment. Given that some people, is anything else moving around? Is the bubble moving around?
Yeah, it works at similar wavelengths of light.
But it suffers from this problem in control.
Yeah.
So the point of your thing is not to get better resolution images, it's just to get lower interference from the non-objective area.
Yeah. So it's called the point spread function, how light impinges on the detector from the optical system that you're looking through. And all optical systems scatter light to large radius from where the actual point source, the center of that point source hits. And depending on how much we call it the wings of the point spread function, what fraction of that light is scattered around, if it's high enough, it will mimic or lead to a systematic uncertainty over the entire image. You just cannot calibrate it out because you do not have perfect knowledge of how much light is being scattered out. If you had perfect knowledge, then you can calibrate it out, just remove this big point spread function even though it's this big, and remove it, but it's really hard to do that.
So the point spread function is fatter, but lower in size.
Yeah,
Than a
that's right. So the small aperture means that it's going to have a pretty wide width. With Hubble, you get a much smaller core of the point spread function. But Hubble has a lot more light scattered than large radius on the image, and we're going to minimize that both on the ground and in space. Yeah.
Okay, good. Thanks very much.